correctly?
Okay, so you've got it. Okay. We're right. Oh, and head of school format. That's wow. No, we have efficiently. Really getting it.
I mean, I this for our own seminars. I feel like seeing tricks about Zoom or like over them.
Okay, I'll start. So, I'm very pleased to welcome Professor Justin Spilker here. I've known him since he was a lad. First year grad student, I think.
I think I was taller than you then too.
And he's always been my closest collaborators and one of my people I've been most collaborate with in my career. There's a rare thing about graduate students. I remember.
Because there's an electrical one.
I did.
I am not good. Am I supposed to?
No, you.
No.
Okay.
You're good. Somebody else in the Zoom.
Everybody else is.
Okay. I think a rare thing as a professor is when you're interacting with a grad student and you're learning from the grad student is very rare. I remember that was definitely Justin. So he did his Iowa State in physics. He went to University of what?
Go Cyclones.
Yeah. He went to University of Arizona where he worked with Dan Roney on South Pole Telescope Memory Galaxies, Army Department. Then went to Austin as a postdoc as a Harlan Smith fellow actually. Then he got a fellowship which he's UT Austin, and then he started at Texas A&M in 2020 as assistant. So either way, we're a minute early using that.
Okay. Okay, yeah. Thanks, everybody. It's a real pleasure to be here. I'm assuming that Zoom collides okay, because I haven't heard any complaints in the chat about that. I think great. Okay. So, what I want to talk to you today is a little bit about a large program that I've been working on for a number of years now. What our basic is trying to do here is trying to reveal a lot of details at high spatial resolution about galaxies in the early universe. And so I'm gonna do something I have done all my intro classes with my undergrads, which is play a little game called What can you tell me about the galaxy? This is a galaxy that probably many people have seen before. I will sit back and make you actually talk. So feel free to shout out. What do you know about this galaxy in this picture? Yeah.
It's got spiral arms.
It has spiral arms. What else do you know about this galaxy?
I'm gonna slide.
No, I just made this slide yesterday. Yeah.
Got a little buddy.
It has a little buddy. Yeah, we got a little buddy. Or what else do we know? It's star forming. How do you know it's star forming?
Red.
It's got some red, like 2. That's H alpha. How else do you know it's star forming? Spiral. Okay, so you're basically saying it's a spiral galaxy, so it's star forming. What's another way you can tell that it's star forming?
Lots of blue light.
Lots of blue light. Yeah. Got some blue light there. How do you think this galaxy is moving? What is its dynamic kinematics? Probably spinning, right? Yeah. So you can probably imagine this is a spinning, rotating galaxy. So this is all true. This is M51. The galaxy. Yeah. One more.
Sorry about it. There's a little audio issues.
What do they?
I need to switch the laptop.
Next. Everybody.
And okay. Zoom, is that better? Audio?
Yeah.
I feel like somebody else has Zoom on.
Yeah, that's good.
Okay, cool, great. Okay, sorry about that, Zoom. I'll try and stay close to my laptop so that you can hear me. Okay, so this is the Whirlpool Galaxy. It's a very famous galaxy, M51. It does have this merging companion there. As far as we know, that companion has not really impacted the kinematics of this galaxy yet. If you look at the velocity field of the main spiral galaxy, it looks like a beautiful rotation curve. And this is a pretty typical kind of massive star-forming galaxy today. Here's another galaxy. Maybe I'll have to click again to get this to go. This is a similarly massive typical star-forming galaxy at a redshift of about 2 from about 10 billion years ago. What can you tell me about this galaxy? I've tried to change to some imaging filters that are still roughly similar to what we had before. What can you tell me about this galaxy? Yeah.
It looks like it has spiral arms again.
Yeah, it still kind of looks like it has some spiral arms there. What else?
Got a little fluctuating winking thing in the middle.
I'm pretty sure that's the projector because this is not a GIF. I don't know what's up with that. That's the variability of the. No, I'm just kidding. Yeah, it's red in the middle. Sure. What do you notice sort of structurally about those spiral arms compared to the last one? Yeah, it looks pretty clumpy, right? So that's kind of unusual. So those spiral arms are less defined. We're still seeing that star formation, but in a clumpier fashion. This was a typical star-forming galaxy for redshift 2. Here is a typical star-forming galaxy for about redshift 4.5, about 12.5 billion years ago. What can you tell me about this galaxy? Yeah.
He's got spiral arms.
I really have no idea. Like this is JWST imaging, right? So this is as good as it gets. If there are spiral arms in there, right, like it's very hard to tell. We're seeing these very large clumps. This galaxy is almost entirely blue. We don't see a lot of that underlying red light that we saw in either of those two previous cases. And so that's an interpretation that basically this galaxy is very young. We don't have a lot of that older underlying stellar population. And so, yeah, this is not visibly, this doesn't look like it's a disk. It's not obviously going to be something that's rotating. Yeah, Kirk. So we don't know. It's 2 clumps, right? These are just large clumps. And so that's one of the things that actually we know about high redshift star formation now, is that as you go to these earlier and earlier times, galaxies become more clumpy. Part of this is just basically because the Jeans length, essentially, if you think back to your ISM class, becomes these much larger sort of size scales. So whereas the Jeans length in like the Orion molecular cloud is like 1 parsec, when you get to high redshift, because the gas fractions are higher, the turbulence velocity dispersions are much higher, that length scale for typical star formation becomes very large, comparable to the size of galaxies. And so after all of this work with things with telescopes like Hubble or with JWST, we actually can trace out pretty well the evolution of what a typical massive galaxy looks like in their starlight from the early history of the universe to today. At least in the nearby universe, and there are people in this room who have done this, we can also map out the cold molecular gas, the cold gas within galaxies on sort of similar small scales. Here is, if I've gotten that overlay correct, the map of the CO emission, which traces that cold molecular gas in this galaxy. And so what that lets us do is essentially try to connect the molecular clouds that stars are forming out of together with those young stars that have just formed from clouds, and along with comparing those to the underlying older stellar population. And so that's really helpful for us to understand the life cycle of stars and star formation as galaxies evolve. That becomes super expensive as you go to high redshifts. So here's our typical massive galaxy at a redshift of about 4.6 again. If I show you the best available map of the gas in this galaxy, it looks like this. There it is. And so we just really aren't at the level of detail when we're trying to look at the fuel for star formation at these high redshifts. We don't have a good sense of, is the star formation clumpy? Is the gas clumpy? It's hard to interpret, I can't really take a velocity map of something that has 0 resolution elements across it. So I don't really have a good sense based on the data that we have here, is this galaxy actually rotating? Is it, a merger? I don't have a sense from the kinematics of this galaxy of that question of the same way that I could do at much lower redshifts where galaxies are larger and brighter as well. And so what that winds up being, just for like a point of context here, this is a plot that like every extragalactic astronomer has to show. This is the only time I'm going to show it in like cartoon form. It's basically if you ask yourself, like, when did most stars in the universe form? Most stars in the universe formed actually at about redshift of 2. By the time we got to about 10 years ago, we could have a really full, detailed kind of accounting of the cold gas, the dust, the young stars, and the existing stars, the H2 regions, basically almost whatever you could want at these sorts of highly resolved scales, let's say a few hundred parsecs. We could do that at redshift 0 with these telescopes like Herschel, with Galaxies, or with ground-based telescopes with Hubble. What we're trying to do now is essentially push this level of detail, this level of spatial resolution, out to the early universe. And so because we're now looking at high redshift galaxies, we have to shift the wavelengths that we're using. And so that cold gas part is going to come now from ALMA. The rest frame UV is going to come from actually the near infrared filters of Hubble, which is kind of funny to think about. And then now with that JWST exists, we can now have access to the rest optical. So we can get the stellar continuum and we can get those nebular lines. And so what we would like to do is essentially make that connection across redshift of what a typical massive galaxy looks like just on its sort of small resolved spatial scales. This isn't just sort of like an academic question. As it turns out, we also expect from theory that the way that galaxies form over time has changed drastically. So these are two movies that are essentially showing you, I was not able to get like the time axis of these to like line up in any way. So apologies for that. Essentially what a typical massive sort of disk galaxy looks like, either at low redshift, this one is evolving from about redshift of 0.9 down to 0.1, or at about redshift of 4. And you can sort of just see visibly with your eyes the differences between these galaxies, right? This galaxy at low redshift has a very strong disk rotational component. There's still gas flying around in all directions, but the kinematics are super disky. It looks like a frisbee. Whereas this galaxy on the right, is much more clumpy. The gas is everywhere. There's a lot of chaos going on there. There are some times when it looks like there's rotation. For example, after some minor merger falls in, you induce some rotational signature, but it doesn't necessarily stay that way over long timescales. Yeah. So these are basically typical massive galaxies for their epoch. So the one on the right is lower mass than the one on the left, but that's because galaxies like the one on the left are very, very rare at the time of the right. So
are they the galaxies on the left? Look at massive galaxies.
Yeah, so we're not at the point where we could look at, for example, like a Milky Way progenitor across redshift, but we can see sort of like, you could think of it as like, let's look at the top 10% most massive galaxies across redshift, right? And so the galaxies are more massive as we look at lower redshift because they've grown more.
I guess I'm asking, you could mention massive right side.
Yeah. Good question. Yeah, actually, I haven't done that comparison either. Yeah. We could definitely do that. Okay, so this is kind of the prediction from theory is at low redshift, we have these very nice ordered settled disks. At high redshift, we have chaos. Brief glimpses of rotation, perhaps, but like not necessarily all the time. There's gas flying around everywhere. There's gas inflowing. There's gas outflowing. As a response to basically the processes of galaxy evolution in this way. And so some of the questions that I'm going to try and answer for you today are stemming from this idea that we can now actually have access to the resolved structure of galaxies in their cold gas, even out to these very early times. And so some of the questions we're going to try and talk about today are about their kinematics. So is a typical galaxy at redshift 5 rotating the same way that a typical massive galaxy at redshift 0 does? Is its level of rotation compared to turbulent gas motions? How has that evolved over time? How many of these systems are interacting versus not interacting, and so on. We can ask simple questions about the morphology, like I just did with you guys. We just looked at some pictures and shouted out some things that we learned about, M51 from that way. So, where does the gas live? Where is the dust? Where is the stars? How are those distributed relative to each other? How clumpy are these things? How smooth are they? We can ask questions about the ISM of these galaxies. So we're going to be looking at cold gas tracers and the dust as well. These are both components of the interstellar medium, the gas. And so we can ask questions about, where did dust form? Perhaps where is the gas living? Is the gas being removed or inflowing, or whatnot? And we can also ask questions about these sorts of outflows. So if I have a supernova explode in a galaxy that sets off a bomb, starts to drive gas outwards into intergalactic space, can I see evidence for that happening? And what impact do those outflows have on their galaxies as time goes on? So as we're sort of starting here looking at these high redshifts, We started off, this whole game became possible basically because of ALMA. ALMA is by far the world's most sensitive telescope at millimeter wavelengths. And so before that thing turned on, there was no hope of doing this. It was actually one of the sort of early ideas that people had to use ALMA to look at the cold gas and dust in these high redshift galaxies. That started off in about 2015. This was a paper from Peter Kapak, where he observed 10 galaxies at about redshift of 5 in the C+ line of ionized carbon. It's a rest frame of 160 microns. We like it because it's stupidly bright. It's the brightest line in the far infrared. And so by golly, it better be useful for something. That would be great. As time went on, people started to do large surveys for this. So one example of that was a large program called Alpine that ALMA ran. They tried to detect basically the C+ line in almost 100 of these high redshift galaxies at like 4 to 6, redshift 4 to 6. And so what I'm going to talk to you mostly about today is trying to extend that work to higher spatial resolution. So trying to resolve these galaxies down at like kiloparsec-ish spatial scales and understand what we can learn from that. And so the program that I'm going to talk about is called CRISTAL. The acronym is super contrived, is the C+ resolved ISM in star-forming galaxies with ALMA. Yeah, the acronym like trails off in terms of like fidelity to the word. And so to give a little overview of this program, this was a large program during ALMA cycle 8. We took data mostly in 2021-ish, with a little bit that carried over into 2022. We wound up getting a grand total of like 150 hours of new time. And as it turns out, there was also a few existing projects from the archive that we could swipe data from and sort of combine that with our sample. So I'm one of the co-PIs of this program. The overall PI is Rodrigo Herrera Camus, who's in Chile, along with these other folks from around the world. And so I think grand total we're something like 50-ish people on this team now from a number of different countries, which is fun. So the tracer that we're going to be using for this program is the C+ line, that far infrared fine structure line. We picked it because it's bright. That's basically the main reason. So that's the useful part. We're aiming to get down to spatial resolution of like 0.1 to 0.3 arcseconds, which is roughly 1 or 2 kiloparsecs. And we originally proposed for this sample to be like 19 typical main sequence kind of galaxies. I'll show you what that means in a second. So the selection was pretty straightforward. We were picking things with known redshifts that had already been detected in C+, so we knew how bright it was. So we knew how long we had to waste spending ALMA time observing these things at higher resolution. And then we basically just required that they had HST imaging, and then we made a mass cut. The nice thing about this is that all of these galaxies are in deep famous fields, quote unquote, and so they predominantly also have imaging from JWST, as well as near-spec IFU spectroscopy, which I won't really have time to talk about today, but I can. So here's our actual sample at the end of the day. This is a plot that shows the stellar mass of these galaxies against their star formation rate. This gray band down the middle is what extragalactic people call the main sequence of galaxies, because we like to think of galaxies similar to stars as being like a one parameter like object, even though that doesn't make any sense. But the gist is that, you know, all of the galaxies in this sample are very typical, very normal for their time. So they have star formation rates that roughly accord with the amount of mass that they have. Yeah, question.
Simple question, but how do you actually get the stellar masses?
Yeah, so at the start of this, it was based on the imaging that was available. Again, these were in deep fields, so we had everything from like rest frame UV out into the optical from Spitzer. And now we're actually getting better stellar masses out also from JW. So yeah, so I believe that these actual masses are from the previous data. This does not include the JWST alterations to the fits, but that's something that we're working on for sure. You might also like count these circles and feel like there's more than 19, which is true, because as it turns out, as we were doing the observations, we discovered some new galaxies in the same fields as the ones that we were looking at. So some other objects in the field. There's also 2 very highly dusty star-forming galaxies, the kinds of things that Joaquin and myself and David and other people in this room also study. There were also 2 of those that happened to be in our fields. And so at the end of the day, we have a grand total sample of almost 40 galaxies with this sort of kiloparsec spatial resolution. And so that's been really powerful. And so I'll show you a little bit of a demonstration of kind of what we have aimed to gain here. So here, this is actually that same galaxy that I showed you before, I think. It's hard to tell the difference between a blob and a different blob. So let's just go with it. So this is the information that we had from that previous Alpine program, which was not aiming to resolve in any sort of spatial detail what this galaxy looked like. Image of the C+ on the top and the velocity field on the bottom. So ALMA works basically like an integral field unit. So you get spatially resolved spectra at the same time as you do your observations. Our data, we've now improved on the spatial resolution by about a factor of 10. And you see that this galaxy has now resolved into like this crazy looking structure. We've got a super bright kind of like clumpy structure over there with some sort of diffuse excess C+ emission extending there up towards the north. The velocity field looks kind of like a mess, not obviously like a nice smooth gradient or something like that. That would be signs of rotation. Yeah, question. No worries.
What made it so that you could resolve this better? More time, better?
Yeah. So time helps you, but the resolution of a telescope is lambda over d. And so since ALMA can pick up its dishes and move them, you just basically wait for them to move them farther apart. And then you can re-observe these same galaxies. Yeah, fair question. Yeah. So ALMA is also an interferometer, which means that I can like play around with the resolution after the fact, which is kind of weird to think about if you're like an optical person where your pixels are like literally physically pixels. Here our pixels are made up. And so I can keep playing games and say, well, what if I change how I weight all of those different visibility baselines from ALMA? And I can go to higher spatial resolution still at the expense of signal to noise. And so that's what I've done here. And now you see very clearly that that C+ has resolved into two main bright clumps. And at this level of signal to noise, all of this sort of diffuse fuzzy emission has mostly gone away, which is an artifact of the Fourier transform filtering, which we don't have to really worry about here. Yeah.
Actually, that little blob in the south, is that real or is that just an artifact?
Unclear. There's no counterpart to it in JWST imaging. So if it's real, then it's just like gas that's there, which we have seen some examples of. So it's not totally crazy, but we don't know for sure. I knew somebody was going to ask me about that. Okay. And so here's our family picture of what the results from this survey looks like. This is 300 hours of ALMA time. Are you not impressed? These are scaled such that basically the same physical size is common between all of these. So this little scale bar is 6 kiloparsecs there. And so you can already start to see sort of a wide variety of the morphologies, the structures that we're starting to get out of this survey. You can see some that have this like huge extended structure. You see some doubles that are probably mergers. You see some cases where there's like gas extending over large scales. Maybe that's a galaxy, maybe not. I don't know. We were trying to make this to look a little bit like this other famous image. This was an image that ALMA made of a bunch of protoplanetary disks. Where in this case, like all of these gaps that you're seeing are places where like maybe planets are forming out of these disks, but maybe not. Apparently that's like contentious. I didn't realize that. So ours doesn't look quite as nice as that. Our galaxies are maybe not quite as like ringy and spirally, and they don't have quite that same level of visual appeal, but that was the idea. So the great thing about doing all of this C+ work is that we can also get the velocity fields out of that C+ line. And so here's the family portrait version of that, where now you can sort of see the diversity of kinematic profiles that we see, where you see some that have this really nice red to blue velocity gradient. That's kind of what you expect for something that's rotating. One side is coming towards you and the other side is going away from you. But you also see some that are just like kind of a mess, right? So no obvious signs of rotation there. So I can show off just a couple examples of these. There's one galaxy from our sample. On the top left is just the C+ integrated line. So just add up all of the line luminosity. Top right is that C+ velocity field. The lower left is the continuum emission that comes underneath the line. This is mostly from dust. And on the bottom right is including the JWST NearCam images with the C+ on top of it. And so this galaxy is CRISTAL 6. It's the 6th one in our survey. And in this case, you can see that basically the C+ has resolved into these multiple several clumps, each of which basically has some underlying counterpart in JWST. And so that tells you that there are stars associated with this gas, aka these are probably galaxies, separate galaxies. And so this is one that is most likely some sort of merger interacting system, where now we know for sure that all of these little clumps that we see in imaging in JWST are confirmed at the same redshift because we detect them in the spectral line. Yeah.
Split into continuum C plus line.
Yeah, so ALMA has a pretty wide bandwidth and C+ is narrow. And so basically all you have to do is say, okay, C+ is there, I'll just ignore that and get everything else and call that continuum. Yeah, yeah.
You'll get this later, but how does the extent of the C plus compare to the dust continuum?
Yeah, so the C+ is, I will not get to that. I took out the slides on that because I'm pretty sure I'm going to go long, but I will, not go long. Yeah, so we know basically that the C+ is more extended than the dust. The C+ is more extended than the UV. The C+ is more extended than the optical. Basically, C+ is more extended than everything. Yeah.
So that seems to be like universally true for these high-redshift galaxies, or?
Yeah. Yep. Yeah, the effective C+ radius, I want to say we found was like 50 to 100% larger than the UV continuum. So yeah. I think, so do you have a question too? Yeah.
Why is there no dust in the galaxy on the left?
It's probably just a lower mass galaxy or a less dusty galaxy. So, so the amount of dust in a galaxy, one thing that predicts that is just mass. So a more massive galaxy has more dust, and also a more metal-rich galaxy typically has more dust. And so it could be that that galaxy kind of in the upper part is just lower metallicity and lower mass. And so we can see it in the gas in C+, but we can't see it in the dust continuum. Yeah, fair question. Sure.
One more thing. I think the rebel sources, they have galaxies that are seen in C plus and not detected in continuums.
Yeah.
Have anything like that.
Yes, there's one.
But I think in the ALMA as well.
What do you mean? So we detect them in dust, but not C+?
Like
Or what do you
see
mean?
the peak, but otherwise you don't see like a lot of signal from the dust in ALMA.
I mean, that is what this is, right? That's one that we see in the,
Okay.
that's C+ that we see, but there's no continuum underneath it.
Like hallucinated the product hash. Yeah.
I cannot speak to your hallucinations. Okay, here's another fun one, I think, out of this. This is crystal 13. In this case, also, we see that the C+ breaks up into this kind of multi-clumpy kind of morphology. All of the dust is located in the southern part. That's not super surprising because that one is way brighter. And so dust is much harder to detect here. In this case, that plume towards the north of C+, there's nothing underneath it in JWST. So it seems like this is just gas that maybe got ejected as part of an interaction, or maybe it's an outflow. Maybe it's even inflowing, we don't know. But we do see also cases where the gas is, kind of existing out in the circumgalactic medium around the galaxies and not necessarily within the galaxies. I also like the JWST image of this because it's like this crazy wonky structure. I'm actually not even sure that both of these things are at the same redshift. So that's something that we're going to try and figure out. Yeah. It's just too faint. Yeah, exactly. Yeah.
AGN destination.
Unfortunately, no. Yeah. So the whole sample was selected to avoid AGN originally. But that was based on like UV data. So there's no guarantee that there's not AGN in these galaxies. We are going to try and answer that with the JWST IFU spectra, because then we can get the classic BPT lines. But that's work that we're just like barely starting. So yeah. Okay. Cool. Here's another one. This is one of my personal favorites. This is crystal 8. In this case, the JWST in the background breaks up into like these like 8 or 10 different little stellar clumps. Because we have such fantastic quality data from JWST available for these, I can estimate the ages of each of those clumps based on their spectral properties and their photometric properties. And so I'm trying to basically summarize that over here on the right, where these blue kind of clumps are the younger ages. Then we've got some that are a couple 100 million years old that are a little bit older. All of that gas that we trace in the C+ is kind of like interdispersed in between all of those clumps, which I think is pretty fun. So it doesn't necessarily look like the clumps are forming out of the gas. It looks like these clumps are old enough now that they have cleared the gas away from them. And so you don't see the gas where those clumps are predominantly. You typically see the gas in between where the clumps were, which is kind of cool. One of the fun things that you can do with ALMA is to plop down little apertures on your C+ map and take the spectra out of those individual spatial regions. And so here are 4 of those, a couple of them that are centered on those northern clumps, and a couple of them that are centered down in the southern part of the gas. And what we see in each of those 4 regions is that there's some excess high velocity gas in the regions of those clumps, which we can kind of interpret as evidence of an outflow of gas being driven out of those clumps or impacting into the gas of the clumps. Yeah.
With that beam size, how many pixels are you capturing in those apertures?
Yeah, it's basically like one resolution element within that aperture. Yeah. Mm-hmm. Okay, cool. Yeah. Yes, I think I will even show it to you soon. Yes. I don't remember that 100%, but I think I will. Yeah.
Okay.
Sure.
But you like in the text you say that this is an example of like something in a normal galaxy. But,
Mhm.
like, that doesn't look normal to me. So what's normal about it? Like, is it like?
Yeah, I mean, the normal part about it is that given its total mass, it is forming stars at basically exactly the rate that you would expect it to. So we don't really know what a normal galaxy looks like at these redshifts.
Okay.
You know, we do think that they were clumpier. And so that's why you're going to see a lot of galaxies that look pretty clumpy, is because that was normal.
Okay, so it's like compared to other galaxies. Like
Yeah, exactly. So these are typical for the time. They are not, if this galaxy just like transported magically to today, it would not look normal to us now. Yeah. Okay, so to come back to our open questions here, I am glad that I didn't plan to talk about all 4 of these. Instead, I'm going to focus on these 2. We're going to talk a little bit about the kinematics that we're getting out of this survey, and then about the outflows. And hopefully, even that will not have me go over. We'll see. So I'm going to talk about kinematics first. And for both of these, actually, I'm going to play a little game where I show you kind of like a case study, like an interesting example, something that we've kind of like looked at as one interesting object, and then kind of follow up with, you know, the overall trends that we get from the full sample. And so for the kinematics, this is work led by my now postdoc at A&M, Anna Pazos. She finished this work up as part of her PhD with Manuel Aravena at UDP in Chile. And so she was looking at this particular galaxy, CRISTAL 5, which is one that I showed you before. It has this huge extended amount of C+ up here, but most of it is concentrated down in this kind of clumpy region down here. The JWST is not, I would say, like especially elucidating here. It's not like obvious what this is. It looks like, you know, maybe a single disky kind of galaxy sitting there, but, you know, not especially obvious what that thing is. The velocity field of this system looks like this. Definitely doesn't look individually like some rotating system, so there's probably multiple components involved here. And so what she did is essentially she's going to take a slice across through the data cube of this image and make what's called a position velocity diagram. And so basically say, you know, at this position along this pseudo slit, what would the spectrum of the C+ line look like? What would it look like here? What would it look like there? What would it look like there? And so on. And so when you do that, this is what that ends up looking like. Here's that position along the x-axis and then the velocity, so AKA the spectrum along the y-axis there. And now when you look at it this way, you can kind of see a little bit more clearly that there are 2 components to this. There's a southeastern galaxy that kind of is dominating the emission down on this part. And then a northwestern galaxy that's kind of dominating the emission up here towards the northwestern area. Yeah.
So on the last slide,
Yeah.
I noticed that you had a threshold, like, you know, a min-max threshold and velocity field of -80, +80, whereas in others you have like -120, 120.
Yeah.
That being said, is there like a reason that you excluded like the range from like 80 to 120? Because it seems like this velocity map sort of excludes what happens like towards like the top left of like this main like lobe here.
Right.
So do you have any what's going on with like that secondary lobe over there?
Yeah, so the reason that this part up towards the north doesn't show up in this velocity map is just because the signal is so low that basically like it's if you were to try to put that up here, you would basically overwhelm yourself with noise. And so this one goes from -80 to +80 because that's roughly the line width of this particular galaxy. Other galaxies have different line widths, and so sometimes it's -120 to +120 or -200 to +200. It just depends on whatever the line width of that particular galaxy is.
So then
Yeah.
would you probably, it'd be safe to say that, like the velocity maps, like thresholds for like what signals you get from the velocity maps are not indicative of what is like typical for galaxies in time? Because I guess like based on different, based on like whatever, range of redshift galaxies you're looking at, you say that you're looking at galaxies that are typical for the time. Right?
Yeah.
It's like, what, I guess, to be fundamental, what sort of like factors go into defining what is typical for a galaxy at this time? And how is the velocity field, like, sort of, how is the velocity field affected by typicality?
Yeah, so we didn't know how the velocity field impacted things like that. That was one of the main reasons that we wanted to do this survey, was to understand what is the velocity field of these galaxies? You know, what do they look like in typical terms? I mean, things that impact that range of velocity that you see, like if you just imagine like the same disk that's rotating, if it's rotating edge on to you, you will see a wide range of velocities because you have very blue shifted and very red shifted. But if that galaxy is face on, then suddenly, you know, you wouldn't have to go -200 to +200. You could get away with something much narrower because all of the rotation is in the plane of the sky and you can't observe it. And so there you would have a much more restricted range of velocities where you actually can see C+ at all, not due to anything related to the galaxy itself. It's just due to its inclination. For these, we don't necessarily know in advance that these are disks. And so some of them, you know, might have a different range because they are just different. Yeah, they don't have to be the same. Okay, so within that position velocity diagram, Anna was able to show basically that now it's pretty clear that there are two components to this system. And in particular, this one, the northwestern galaxy there, has this nice kind of like smooth velocity gradient along it. So in other words, as you step along in position, you see that velocity slowly march towards more and more redshifted redshifted values. And that's actually exactly what you expect for rotation. And so if you just looked at this velocity field, you would say, obviously this galaxy is not rotating. That's ridiculous. This does not look like the velocity field of a rotating galaxy. But this particular component of it alone actually does look like a rotating galaxy. And so after a lot of hard work, Anna was able to separate out these two components using diagrams like this one. And so here's what the velocity field of that northwestern galaxy looks like if you remove the contamination from that other object in the field. And now it looks like a much more smooth kind of progression, blue shifted on one side, red shifted on the other. And so she took it a step further and fit this velocity field with a kinematic model that basically tries to assume you know, an amount and distribution of mass in stars and gas and dark matter or whatever, and try to reproduce this kinematic map. And so that's what that looks like here. This is the rotation curve of this particular galaxy. This was done using a code called Dismal Pi. For those who are like aficionados of this field, this was the MPE group's code, which they actually finally made public after like 20 years. So it exists. She has used it. A number of other people have used it. And it seems actually pretty powerful. So I don't know that I can personally recommend it, but definitely people are getting good results out of this. And so what she was able to show here, this is essentially the rotation curve that we observed. But we think that if you were to account for the observational effects, the resolution of the data in both space and velocity, that the true rotation curve of this galaxy would look something more like this. Yeah, question. Yeah, so we're trying to account for inclination, and here we're doing the stupidest possible thing, which is to look at the JWST image, and if it's an ellipse, say, here's what the axis ratio is, and relate that to an inclination. Yeah, we don't have an independent handle on the inclination, so that's kind of what we had to do. And so I think this is kind of like an interesting and good example of a galaxy where it didn't look obviously rotating at first, but when we were able to explore it in a little bit more detail, we could see that there was some rotating disk signal here. And so this was kind of an interesting case example to start with. To extend that to the full sample, this was work done by Lillian Lee, who's a finishing PhD student at MPE, working with Natasha Forster-Schreiber. She basically extended that analysis that Anna had done to the full crystal sample. And so what I'm showing you here is now those same velocity fields as a function of stellar mass, and then essentially how far away are they from the main sequence. So galaxies above this line are slightly more star forming than a truly typical galaxy. Galaxies below that dashed line are slightly less star forming than a typical kind of galaxy. And so again, kind of in this, you can see some galaxies where we have these really nice gradients, but you can also see others where it just looks like a little bit of a mess. And so the strategy that Lillian took on this was to say, well, I don't actually know which of these are disks and which of them aren't. So I'm just going to take my disk model and fit them all, and then look at the results and ask what question, ask what the results of that are. And the reason for that is to basically say, we don't want to, only impose a disk on the galaxies that we look at them and we're like, oh yeah, that's a disk, fit that one. We're trying to basically try to be a little bit less biased here and use the same code to fit the same data to the same galaxies, regardless of whether we know it's a disk or not. What she does after that is to basically say like, okay, well, obviously a disk was a terrible fit to this galaxy, so I'm going to say that one is not a disk. Whereas maybe she got a really good disk fit for this one, and so she'll say, okay, yes, that one seems like a disk. And so she plays that game. What she finds is that essentially somewhat less than half of the galaxies in this sample are disks at all. So depending on how you want to be like conservative, our best disks or just disks, that fraction of galaxies that are disks at this redshift ranges from somewhere between 20 and 50%. Which actually I thought was kind of interesting, matches what you get from visual classification based on optical imaging from JWST. These black points are a compilation of image classifications based on the Sears field from JWST imaging. And here, their definition of a disk is basically like, does this have a Sirsic index of 1 if I fit the light profile? Our definition of a disk is, does it have a velocity field consistent with rotation? So I was actually like stunned that these two agreed as well as they did. Yeah.
Great example, it showed up with a non-disk in this field, right? Because we didn't subtract out just like a point.
Yeah, so exactly. And so we have to look at basically every single one individually and try to understand like what is it that I'm actually looking at here.
It's an upper limit of 0.50% disks.
That would be wouldn't that be a lower limit of disks? Yeah, yeah, right, exactly. So probably the true answer is somewhere in between these. Yeah, exactly. Yeah.
Since you mentioned that these are, well, since you see a lot of C+ clumps, is there anything you can do with the C+ clumps and kinematics, like tomb ray analysis and stuff like that with these galaxies?
I think we can. We haven't done that in this kind of formalism. She does look at the tomb ray Q parameters for the disk as a whole, but not within clumps on like a resolved kind of spatial scale. Yeah. Actually, I think I'll show that to you in a second if I remember right. So the rotation curves of all of those galaxies that are disks are shown here. We actually have a pretty wide variety. This is like an interpolated model version. This is not, our data are not actually this like high quality. This is coming out of those kinematic models. And so if she then goes and says, okay, well, what do the kinematics of these things look like? How much rotation is there compared to turbulent velocity motions? She wound up with this plot, which I know is busy and confusing, so I'll try and walk us through it. Essentially, our points are these hexagons in green here. This y-axis is essentially the ratio of rotational motion to turbulent motion, where typically what people will do is say, well, if V over sigma is greater than 1, then the rotational support dominates. In other words, this is something disk-like. Whereas if this is less than 1, then the turbulent motions are dominant over the rotational motions, and so it's not really like a rotating system very much. So one thing that had been done a lot leading up to ALMA was to look at many galaxies in the ionized gas phases, which are predominantly these triangles in here. There was like hundreds of hours of VLT time spent with Symphony and Symphony AO mode to try to measure the rotation curves of galaxies at redshifts 1 and 2 using H-alpha, which is an ionized gas tracer. You might think that maybe the kinematics of the cold gas are different than the ionized gas, and so that's why she wanted to distinguish between these two. You might also notice there's a few other galaxies here which have very, very high values of V over sigma. Those are actually galaxies from the SPT sample. We got scooped on that project, much to our shame. It seems like these are now relatively agreed to be somewhat high, possibly because they declared that these were disks and then tried to recover some disk kinematics from that. So our galaxies, we find much lower levels of rotational dominance, which I think is kind of interesting and not necessarily what I would have expected if you asked me 10 years ago. So yeah. Okay, so break time. Other questions about kinematics? There've been like so many questions, which is fun. Yeah. Yes, so not for our sample because we're not done with that yet. We just got the data in like November, so we haven't done that yet, but we will. I hope we will do that. Yeah. Yeah, so the peak is typically like 15-ish, I would say. And then as you go to sort of high velocity, since the line is getting fainter, it declines from there. So the nice thing about this code, Dismal, is that it's a fully forward model kind of code. So you basically like generate an artificial disk and then fit that to the data that you have. It's not trying to like do the backwards question of saying like, okay, well, here's my like rotation parameters, and this is the disk that I would get from that. So it's like a relatively fancy code, I would say. There's a reason that MPA sat on it for 20 years. Yeah. Okay. Well, in that case, I'm going to scooch on over to the second part of this, the last part of this, to talk about outflows, which is something that I've been interested in for quite a number of years now. So the way that we used to look for outflows in galaxies like this was because your data is pretty crappy in quality, you can't really see an outflow in an individual galaxy. So what you're going to do is just stack the spectra of as many galaxies as you can. And try to look for evidence of broad line wings. So high velocity emission at such high velocities that it can't really be from like, mergers or anything else. It can't be from rotational motions. And basically say like, okay, well, that's my outflow signature. And so this was the example that was done from that Alpine large program. This was the low resolution precursor to CRISTAL. And in this case, they stacked, I think this ended up being like 30-ish galaxies. And indeed, they saw evidence for this kind of broad line wing there. It's not very bright, and so that's why you had to do this stacking experiment to try to pull that out of the noise. But the velocity extent, this emission kind of extends out to like plus or minus 500 kilometers per second. That's way higher than you would expect for any sort of like typical disk galaxy. And so that was kind of why they were asserting that this was probably due to outflows. If you want to turn that into an outflow rate, ask how quickly mass is being driven out of the galaxy. You can basically do something like this. This is basically just dimensional analysis, which is the best kind of analysis. So the mass outflow rate is basically just the outflow velocity times the mass of the outflow divided by the size of the outflow. That will wind you up with something in solar masses per year. So the way that you would do this is you would measure that outflow velocity from the width of your broad line wings. You would assume some size, just pick a number, I don't know, a couple of kiloparsecs, that seems reasonable. And then try to assume some conversion factor to go from luminosity to mass. There are some people in this room who have done this in the past to try to convert the luminosity of the C+ line into a mass of cold gas. In practice, this depends on things like the gas density and temperature and metallicity and so on. And so the two sort of advances that we get from CRISTAL are that one, we can now do this in individual galaxies. We don't have to do this from a stack, although I will also show you a stack. And instead of assuming a size, we can actually just measure that. And so the case study for this one that I want to show you is this galaxy. This is work that was done by Rebecca Davies, who's I think she just got a permanent job like a month or two ago in Australia, but she's currently a postdoc at Swinburne. She looked at this galaxy, CRISTAL 2. And if she plays that game of plopping down a bunch of apertures and pulling out their spectra of this galaxy, in each case, what she finds over all of these individual sort of couple kiloparsec regions is that there is this broad component to the line profile. In this case, because we know what the rotational field of this galaxy is supposed to look like, we know for sure that this broad emission is not due to, for example, non-circular motions or I don't know what else, minor merging or anything like that. So this seems to be sort of a bona fide outflow. And so one of the ways that she analyzed this was to basically plot this on a plot of the velocity of the outflow against the star formation rate surface density. So basically like how many solar masses per year per square kiloparsec are forming within each of those regions. There was some prediction from theory for what that should look like in terms of redshift 0 starburst galaxies and then higher redshift galaxies that were typical. Those outflow velocities are higher basically because at higher redshift galaxies were smaller and the star formation rates were higher. And so the supernova volume, like, supernovae per cubic parsec or whatever, is way higher as you get to those higher redshifts. Yeah. Yeah, I mean, we're just doing something stupid, which is to say, I can fit one Gaussian, I can fit two Gaussians. Which of these is a statistically better fit? You can play other games too, right? You can say like, okay, well, I know what the velocity field of this galaxy looks like because I fit its rotation curve. So I could subtract off that model and look at what's left. That gets you basically the same answer as this. But either way, yeah. Yeah. Yeah, it's a fair question. We don't necessarily know what the geometry in 3D of this thing looks like. But it's pretty common, at least for outflows in the low redshift universe, to be like biconical. So they're coming out both directions of the galaxy. And so you can imagine that you can see some blue shifted outflow and some red shifted outflow, depending on kind of the inclination of that outflow. Yeah, it doesn't have to be to one side or another alone. Yeah, sure.
This could be a naive question, but
Yeah.
do these outflows from ubiquity of set outflows maybe have anything to do with the extended sequence?
I will talk about that very briefly. Yeah, so give me a second. Yeah.
Conical flow explanation doesn't seem to match with the pattern of.
I agree. Yeah. I'll show you a little bit more in a second. I think this one actually is a bicone, but not for this reason. Yeah. Okay, so if she does that and puts each of these individual regions on a plot like this, what she finds is that the outflow velocities don't seem to have really evolved that much compared to redshift 2. They're maybe like slightly higher than what you would have expected based on the redshift 2 work, but not like dramatically so. So it doesn't seem like these outflows are super crazy. The reason that I think this one is a bicone actually is that we got JWST IFU spectra of this galaxy. And so we can observe things like the H alpha emission, which traces the warmer ionized gas in the outflow. And she can play the same sort of game and ask, well, what's the line width of the H alpha? And there she sees this more kind of like, I don't know, maybe bicone-ish kind of structure. The imaging from JWST has like 4 little stellar clumps in there, and it looks like the outflow is coming basically from this one. Looks like it's being launched from that particular region. And so this is like one of only a couple cases at high redshift where we can map out multiple outflow phases, like the cold gas and the warm gas, in a single galaxy and understand what the spatial structure of those outflows looks like. So she went a little bit one step further and put this on a plot of the star formation rate surface density and the mass outflow rate. And she was comparing this basically to M82, which is a very well-known galaxy in the low redshift universe with an outflow. What she found is that essentially the cold gas phase is like 10 times more than the ionized gas phase alone. So getting the ionized gas outflow rate from the H alpha and the cold from ALMA, it seems like the cold gas phase dominates everything, which actually is very, very similar to what we see in M82, if not even a little bit more extreme compared to that. Okay, so I of course like showed you the best example of an outflow in an individual galaxy. So sue me, whatever. What about the typical galaxies? Well, unfortunately for us, like with a handful of exceptions, there's like 3 solid sources in CRISTAL that have outflows in individual galaxies. They just aren't powerful enough for us to have detected at our typical depth. This was a bit of a surprise to me. I had thought that we were going to see outflows basically all the time. I ran some numbers when we wrote the proposal, and I was like, oh, this will be easy. Not easy. So lesson learned for me. And so what we're going to do is turn back to stacking, but now we get to make some improvements. So this is work that my postdoc, Jack Birkin, has just submitted like last Friday, which was cool. So to show you again, here was the stack from that Alpine sample. This was basically every galaxy that Alpine had. So the advance that we can make here is that since we have high spatial resolution, we can do things like intentionally exclude mergers from our stack. So you might imagine that galaxies are crashing together, gas is being flung every which way, so there's high velocity gas that has nothing to do with an outflow, it's through the interactions. Well, now we can actually try to exclude those. And so that's basically what Jack did. He took all of the maps of the crystal galaxies. We used those kinematic classifications that we already had, which ones are mergers, which ones are not, and basically threw away everything that was a merger. And so the thing to keep in mind, I would say, is that this is probably going to result in a lower limit on the outflow rate properties from this sample, because you might imagine that like a merger triggers a starburst, which triggers more intense outflows. And so we've intentionally gotten rid of all those because we don't have a good way to separate out tidally removed gas from outflowing gas. Yeah.
So first, the bits that you're maybe before, they were basing the premise of the redshift for low enough velocity that they wouldn't sort of appear in the output. So
Say that again?
I might have misunderstood. Earlier you said that you were selecting these outflows at a velocity that was large enough that you're excluding those markers on the vision.
Yeah.
These outflows, I guess, are in the same order or sort of very close to the marker velocity, so they don't have to.
Exactly, right. So, right.
Second thing is you just said that the mergers trigger star formation, but there's a time delay, right? So you can't. There's like a problem.
Yes, I totally agree. Yeah, it's absolutely true, right? And what we know is that these galaxies are by definition not starbursts. So they have typical star formation rates for their time. So this is kind of like out of an abundance of caution. We're still going to throw out all of these interactions because I can't be 100% sure that the high velocity gas that I see is due to an outflow or due to an interaction. So that's why I think this is like a relatively conservative like approach to this. So yeah. Okay, and so that's what he did here. This is a stack of all the galaxies that remained, things that were not mergers, individual spectra, images, and then the stack. And so what he did here was just basically do one of these statistical tests to fit one Gaussian, fit two Gaussians, compare the Bayesian evidence between those two. And in this case, a broad component is preferred statistically for this. But you know, it's pretty weak. It's not especially like strong. So that was the part I think that you know, surprised me again, is that actually the evidence for these broad wings was not very strong. The thing that he could do is further subdivide each of these galaxies into regions that had high star formation rates and low star formation rates. And if you do that, you find that there's basically no outflow at all from the regions that have low star formation rates. It's completely entirely due to the regions that had high star formation rates. Which is actually like exactly what you would expect if you think that the outflows are being driven by star formation. And so you might say like, okay, well, this is like looking at the spectra and looking at high velocity emission. Like, what if the outflows aren't in the plane of aren't along the line of the sight? What if they're in the plane of the sky? This was also David's question about like the extended C+ emission. This was from a paper that Ryota Ikeda did. He's a PhD student in Japan at Sukundai. And so what he did here was basically to say, I'm going to take all of our C+ spatial profiles and fit them in the visibility domain, so I don't have to worry about any imaging parameters, and then stack the results after subtracting off one single component from these galaxies. And so if he does that, this is a plot of basically the UV distance, so Fourier mode, versus the amplitude of the emission. What he sees is that there is no broad emission that would show up here at these large spatial scales. And so it seems like consistent with the weak outflows that we're seeing from the spectra, we also don't really have evidence for this extended C+ component surrounding these galaxies, which I think was also a little bit of a surprise to me. So, okay, so what do these typical cold outflows look like? They're actually pretty weak. The typical mass loading factor is only about 1/2. So in other words, the outflow rate divided by the star formation rate, which of these wins? In this case, it's the star formation that's winning. These outflows don't seem to be powerful enough to actually remove a substantial fraction of the cold gas from these galaxies. So still TBD, like, you know, are these things actually able to influence star formation? I don't know, but they're definitely not ejecting a large fraction of the cold gas mass from these galaxies. Okay, and since I know we're like very close to time, I'm assuming, right, we started at like 1/4. Yeah. Okay. So so then I'll stop here and basically just summarize. This is all results that were made possible, especially by the junior folks in CRISTAL, which has been really exciting to see. A lot of students and postdocs, most of whom did all the work that I just showed you today. The really kind of cool, exciting results that we're getting out of CRISTAL, I think, are still, you know, yet to be posted in the archive, but we're getting there. So seems like many of these Redshift 5 galaxies are not disks. The rotational support is not especially strong, and the outflows are also not especially strong. So, all right, thanks. Excuse me.
Yeah, thanks for the really nice talk. I had a question on the interpretation of one of the galaxies you showed earlier. I think it was CRISTAL 8. It's the one with like lots of different clumps.
Yes.
You sort of give ages for them.
Yeah.
So what I was unclear on is like, when I look at it, it looks like there's young clumps on C2 peaks and off of C2 peaks, and there's old clumps on C2 peaks and off of C2 peaks. So, what's going on?
Yeah, sure. I mean, we don't know the 3D distribution of the gas versus the stars. I would say that, you know, my sort of interpretation of this, if I go forward one little, whoop, there we go, is that most of these, this is off. That's, well, it's supposed to be mine. Oh, this isn't mine. That's yours. That's why it's not working. It's because it's not on and it's not mine. Most of these young clumps are kind of clustered around the outskirts of the gas, whereas, you know, kind of as you say, the older clumps are kind of concentrated more in the center. And so, you know, I don't know for sure that this is true, but it does seem like as the clumps kind of formed, they have cleared their immediate vicinity of that gas. That's kind of the way that I have chosen to interpret this. We don't think that there's any sort of like dust obscuration issues here because the dust is actually super weak. It's like barely 4 sigma and it's right there. So I don't think that there's like some substantial amount of like dusty, obscured, hidden star formation or anything like buried down in this gas. But yeah, it's a fair question.
With the sample, did you reach like the finest resolution and map the program?
No, not even close. Yeah. Yeah, we are kicking around ideas of that. The issue is that to avoid being a duplication to ALMA, you have to like double the spatial resolution or double the depth. And if we double the spatial resolution, then we need like 4 times as much time, which means we're talking like almost a large program for a single galaxy. So some of these are brighter than the typical ones, and so we're probably going to try and focus on those ones. But of course, what you would rather do is focus on the more typical ones, since that's kind of like the point of the program. Yeah.
So in the beginning of the talk, you showed the TMG simulation, of the close by and the.
Yeah.
Redshift. And you should point out specifically that the disk was not much of a disk or rotation in the far ways, but then you showed us that a large fraction do have rotation. And then you were also saying there's a lot of complexity here in the gas.
Yeah.
But then you said there is also this feedback happening.
Yeah.
So how do you bring that together?
Yeah, I mean, I think like if you look at small chunks of time in this galaxy, you could convince yourself that you would see rotation at some particular time. Like you can see that kind of like come and go, actually, right? I mean, it's like galaxy scales, right? So
the side on the right side is 20 kiloparsecs, the left side is 60 kiloparsecs.
right. I actually don't know if that is the full extent of this rectangle or if there's a scale bar that I cropped out of this, because there's like a little gray thing that keeps shrinking as that goes. So I think this is actually a wider field than that, but yeah. And so yeah, I think that's actually one thing that's probably important for high redshift that's much less important at redshift 0 is that disks can form and be destroyed on like relatively short time scales at high redshift. You have some merger come in, disrupts the kinematics, but the gas fractions are still so high that the gas is collisional. You can resettle into a disk fairly quickly after a merger event. And so I think like the competing effects of that feedback and then the disk formation and reformation are probably what lead you to get that, you know, roughly 1/3 of galaxies are disks kind of fraction, where, you know, maybe 2/3 of the time the kinematics are so stirred up that you don't see it as a disk, but the other 1/3 of the time they are settled enough that you can see it as a disk.
But then the other option you showed back out the second of the point, it also suggests there's a lot more complexity that might still be with more rotation on the point.
Yeah, exactly. And so our hope, our prayer, right, is that we have resolved enough into that complexity that we know which ones are disks and which ones aren't. But of course, that's a hope or a prayer. So.
These are not.
Not as far as we know. Yeah. Yeah. Yep.
Seems like.
Yeah, I mean, I think you might. For sure, I would expect that, like with JWST, you could get the O3 outflows pretty handily in that sense from galaxies like this. Sure. I mean, this is a typical star-forming galaxy that doesn't have an AGN, but yeah, and that also had pre-existing HST imaging and was able to get a spectroscopically secure redshift from an ultraviolet spectrum. So, you know, there are definitely like selection biases here at play. And I don't think we know necessarily like what all of those individually have done. But I think these aren't like a weird, as far as I know, not like a weird population of galaxies. Yeah. Good boy. My computer's fan is like, I'm gonna skip to a different slide that doesn't have a video because my fan is like.
Yeah, sure. So
Do you
Justin,
want me to
thanks for
turn
all
my volume
this.
on?
Can you hear me?
Ryan, go ahead.
Yeah, can you hear me?
Ryan?
I'm there. Can you hear me? Oh no.
Oh,
can't
yeah, we
hear
hear you. Oh, we just heard
Okay.
you.
Okay, great. So Justin, thanks for everything. We didn't give you a chance to say much about the dust reservoirs and what you've learned about that. Is there like a punchline you can tease us with?
Ooh, sorry. Yeah, I would say that like the fraction of star formation that is obscured by dust is pretty high, like over 50% of, if you only had the UV and did not account for dust at all, you would have less than half the total star formation. The dust is also much more compact than basically everything else, which I think is kind of interesting. I don't know if that's an issue of heating because you need the dust to be warm enough that we can detect it, or if that's a true physical effect where the dust is actually that compact. But if you go to the outskirts and the dust gets too cold, then it's much, much harder for us to detect it. So,
Got it. Cool. Thanks.
So you were talking about how the United States that seems like a kind of like a stuff. There's one of the things out there. Some of like the things that are on the screen. So the first thing felt that the concentration of a lot of gas coming in the space time because the bucket of gas in the space time is one of the function of the
sure. Interesting. Yeah, okay. I do not actually, no. I think the way that we would try to test for that would be to try to look for, in those galaxies that have interactions, if the rotational axis is aligned with the companion, you know, where then you might imagine that like the infalling companion is torquing. What do you want from me? I'm gonna wait for hundreds of millions of years. Yeah.
I'm gonna follow up on Paul's question about AGN. Because I want to fly off well. I'm wondering if there's any evidence of radio AGN at a low level, maybe if there's any overlap with VLAS or fast low-fi.
Ooh, yeah.
Some people are starting to think that low-level radio gets might couple and generate.
Yeah, we actually haven't really looked at that in any level of serious detail. My impression, sort of naively, is that the radio emission that you expect is going to be much fainter than those kinds of surveys. These are in fields that like the VLA has stared at forever in Cosmos, for example. And so that does go much deeper. And I don't know that we've done a good job of checking for cross matches with the radio. Yeah. And in Cosmos, I think like the depth is like an order of magnitude deeper than VLAS even. So yeah, they spent a lot of time looking at Cosmos. Yeah.
So first of all, you mentioned there were two SMUs in this cycle.
Yeah.
And I was just wondering if briefly you could talk a little bit about how those, do they differ greatly? I mean, I would imagine the multiplication rates they differ greatly, but is there anything else in terms of morphology and kinematics that
I should not have deleted the slides that had those on there. Yeah, one of them was a paper from Manuel Soleimano from last year. So that was one of the dusty galaxies in there. And that one looks like the dusty galaxy is super strongly rotating. There's like two other galaxies towards the south, and then this huge plume of C+ extending towards the north. And he actually interpreted that as, if you've heard of like Hani's Voorwerp, where there's like relic AGN ionized gas, like it has AGN-like ionization ratios, but the AGN is not currently on. He could see that in this extended gas. I'm not 100% convinced by that kind of like time delay kind of interpretation of things. But I thought that was one really interesting example. And it's an example where the dusty galaxy looks like it's rotating much more strongly than a typical sort of crystal galaxy. The other one I don't think we've looked at very much. It's Aztec 1, 3, one of those, like one of the single-digit Aztec sources.
And then I was also wondering, you mentioned there's going to be a public data release. So
Yeah.
say a little bit about what kind of data products are actually available.
Yeah, so we're planning the public data release to basically include images and cubes and spectra. And the cubes are going to have, we've made like so many cubes, different spectral resolutions, different weightings to get different spatial resolutions. We're going to include versus not include this JVM correction thing, which I think you know about, and is like a detail that I promise you don't want to know about, everybody else. So yeah, we're basically going to try and like release everything that we think is going to be useful. We've now joined forces with the Alpine team because it was actually them that got the JWST IFU proposal, whereas we got the resolved ALMA large program. We basically both proposed the same projects to ALMA and then to JWST, and each of us won one of those. And so now we decided to like play nice with each other and not fight. And so that's why we're like trying to make all of these data products like very, very accessible. So.
Okay, final question? Okay, well, yeah.
Sorry, I need a really good.
Yeah. I don't think we have done that yet. I can ask Lillian to make that plot. Yeah. Yeah, I don't know. Yeah, we can look.
Thanks, Justin.